Okay, so next method is the modified version of the Gauss elimination method, and we say it as Gaussian or Gauss-Jordan elimination method. So this is the very simple or very faster converging method as compared to the Gauss elimination method, and it is a very basic process that you have to convert it into in simple words, reduce echelon form, and in other words, elements in above and below the diagonals are simultaneously made zero. Okay, so the solution of the resulting diagonal system can readily be obtained. So in this, you don't have to convert it into the upper triangular form and convert it back into the equation and then step 2 back substitution process. You just have to achieve the solution within the matrix, like elements above and below the diagonals are made simultaneously zero. So within the equation, within the matrix, you get the solution. So this is the basic technique for the Gauss-Jordan elimination method. Okay, so now we do its example 2, because example number 1 we have done it with the previous method. So x plus y plus z equals to 3, and 2x minus y plus 3z equals to 16, and 3x plus y minus z equals to minus 3. So we have to use this Gauss-Jordan elimination. So first of all, we have to convert it into matrix form. So we can convert it directly. Okay, your matrix system, augmented matrix, I am just writing it directly. Your matrix augmented system is 1, 1, 1 and 3. 2, minus 1, 3 and 16, and 3 plus 1, minus 1 and minus 3. So what you have to do, first of all, you have to either you want to convert it below the diagonal is equal to 0 or above the diagonal. It's your choice. So I want to convert this 2 and 3 0, and also below the diagonal this plus 1 equals to 0 eventually. So the first step is I want to convert this with the row operation. Row operations are, first row operation I have to make it change in the R2 minus 2 R1, and the second row operation is R3 minus 3 R1. So first row remains same. 2 minus 2 into 2 is 0. Minus 1 minus 2 into 1, so that makes it minus 3. So make sure that I am calculating it right. You have to be very clear about your calculations, because one mistake can lead to the wrong solution. Okay, 3 minus 2 into 1 equals to 1. Also 16 minus 2 into 3, so 16 minus 6 is 10. Okay, and in the third row you have to do is 3 minus 3 is equal to 0. 1 minus 3 into 1, that makes it minus 2, and minus 1 minus 3 into 1, that makes it minus 4, and minus 3 into 3, so minus 3 minus 9 is minus 12. Okay, so these are the row operations for making the first pivot position below the first pivot position equals to 0. Now we want to convert this below this diagonal pivot, second pivot position, we want to make it 0 minus 2. So what you need to do, simplify the third row. What you need to do, 1 1 1 3 0 minus 3 1 10, and the step I'm just simplifying it. I just divide it by R3 by minus 1 by 2. So that makes it 0 1 2 and 6. Now it's simplified. Okay, now I want to convert this 1 equals to 0. So what you need to do, 1 3 0 minus 3 1 10. Okay, and R3. So if I convert it into this, then R3 is basically 1, and 1 by 3 into minus 3. Yes, 1 minus 1 equals to 0. Yes, my row operation is the right one. Okay, the next row operation is 2 plus 1 by 3. That makes it, if we take the LCM, so it becomes 6 plus 1, 7 by 3. Okay, and the next is for constants. So 6 plus 10 by 3. So if I take the LCM, 6 into 3, 18. 18 plus 10 is 28. 28 by 3. Okay. So it makes it 28 by 3. Now I simplify this row and in the next step. So that makes it, you can do it in within one matrix form. So minus 3 1 10, and the row operation here is 3 into R3. That makes it, you know all the rules for the row operations. So if I make it as 3 into 7 by 3, that makes it 7. And if I divide it by 7, like 3 by 7, what it makes 1. Yes. And 28 by 3 into 7, cross multiply it, that makes it 4. So your R3 is 1 4. Okay, now you have to convert this above the diagonal entries equals to 0. So that's a very easy process. Now you have to first of all convert this 1 equals to 0. So what you need to do is change in R1 plus 1 by 3 R2. Okay, so what it makes, change in R1, 1 plus 0 and 1. Okay, so 1 minus 1 is 0. Okay, and the next step is 1 plus 1 by 3. That makes it 3 plus 1, 4 by 3. And for constant 3 plus 10 by 3. So that makes it 3 into 3. To take the LCM 3, 19 by 3. That's strange. If I'm right, 19 by 3. Okay. Okay. Now to make this 4 by 3 equals to 0, you can relate with R1 and R3 because it doesn't affect these two zeros, and it doesn't affect this one non-zero. It doesn't make it non-zero. So if we proceed towards that, if I want to change I want to make a change in R1 and its third column element. So R1 minus 4 by 3 R3. Okay, so 1 0, 4 by 3 minus 4 by 3 is 0. So what will be the last constant? 19 by 3 minus 4 by 3 into 4. That makes it 19 minus 16 by 3. So 3 by 3 is 1. That simplifies. Okay, I convert this also as in a very simple way within one step. and that is R2. I want to make this 0, so I want to relate it with R3 so that these two zeros can not be disturbed. So R3 minus R2 minus R3 to make the change in the R2 to make it a diagonal above and below 0. 0 minus 3. Sorry. Yes. Okay. R2 minus R3. 1 minus 1 is 0. And 10 minus 4 is 6. Yes. It simplifies. 0, 0, 1, 4. Okay. Very nice. Now your system is solved, and if I in the last step I divide this matrix by I divide this by, say, R2 by minus 3, then it becomes 1, 0, 0, 1, 0, 1, 0. Basically a reduced echelon form makes it eventually in the identity matrix. 2 minus 2 and 0, 0, 1, 4. Okay, so your system is here. I can write it in the transpose form, x, y, z transpose. Basically it's a column vector, so that makes it x has the value 1, y has the value minus 2, and z has the value 4. So that results in very less time, and it gives the solution in a very less time. So that is, you can try by your own self these row operations. All you need is practice of your row operations. So I hope that you understand in this lecture, and in the next lecture we will study further about the LU factorization. That is the basically a very advanced form or detailed form of matrix systems.